Okay, so yesterday we were talking about vectors. We talked about doing some simple operations of vectors, adding, subtracting, multiplying by a scalar, and kind of what all that stuff means. And we'll revisit that when we get to three-dimensional stuff in the next section, I believe. Yeah, next section, there's some 3D stuff there. So we're going to go ahead and pick up from page 5. Instead of going back and reviewing a bunch of things, the important stuff will kind of build itself in our review here. All right, so on page 5, the first thing it talks about is unit vectors. And whether you read ahead or you think about it, what do you think unit vector means? Think about like unit circle. There's something special with a unit circle too. What's special with a unit circle? It is set, it's fixed, right? We know that we have a center of 0, 0 for the unit circle. And what's the radius of the unit circle? 1, okay? So when we talk about units or unit measurements, we kind of have these default things that we're working with. And that's similar to what we have with unit vectors. So when we're working with a unit vector, we've already kind of got the part of it being set apart, taken care of component form. We know component form starts with 0, 0, so we've got that part taken care of. But what a unit vector, really all that means, it's a vector that has a length of 1. Okay, that's what it means to be a unit vector. Okay, so in the next next sentence it says we're going to normalize the vector. It just means we're going to force its length to be 1 there. And we kind of already know how to change the length of a vector, right? What does multiplying by a scalar do to a vector?
Makes it longer.
Makes it longer or makes it shorter, depending on if multiplying by a fraction or a negative or something like that. But it changes the length of it. So really all we're doing when we're trying to find a unit vector is we say, okay, I have this vector. It's got some length. Let's figure out what that length is. And then let's use that to basically make this vector shorter or longer as the appropriate amount needed to make it have a length of 1 here. So what we see with this formula right here really should be kind of understandable if we think about it. V is a vector we're starting with. It's got some length, which is again what magnitude of V means. Remember, this means we're talking about the length of V. And so once we know that vector V has, like, say, a length of 3, if it has a length of 3, we need to take 1/3 of that vector, or divide the vector by that magnitude of 3, which is really all we're doing here. We're just multiplying it by the inverse of its length so that we can scale it to a length of 1 here. U isn't always used for the unit vector, but it's often used for the unit vector, so that's why we have U equals out there. But that's really all we're doing. We're taking the vector, finding its length, and then just multiplying by its inverse, so we can make sure we scale it down to 1 there. This is going to work for any dimension of vectors too. So we're still talking about 2-dimensional, but when we get to 3, the same idea is going to carry through here. So for example, if we got a vector v in -2, 6, first of all, where does this vector start? We're only given one piece of information right now. Where does this vector start?
The origin.
At the origin, okay? So in component form, those little brackets, we know it's going to start at the origin here. So whenever we see these brackets, it means we know we're starting at the origin. Okay, if you want to sketch it, feel free to. It's not something you have to do for this, but it still kind of reminds us of what we're working with. The -2, 1, 2, 3, 4, 5, 6. So there we go. Okay. So to find a unit vector means it has a length of 1. It's possible the vector array does that. In this case, it won't. But it's possible a vector could already have that length there. So the first thing to figure out is just what is the length of the vector that we're working with here. So we need to find the magnitude of vector v. I did mention this yesterday. We're going to go through and do it the long way again just to make sure everyone sees why we have this shortcut here. Since we know it's starting at 0, 0, and it's ending at the point -2, 6, when we go through and do the long version of the distance formula, we're always going to be subtracting 0 from these terms here, which we know doesn't do anything. So from now on, when we go through and find the magnitude of vectors, instead of writing all this out, I'm just going to write that we have that component form squared. So -2 squared plus 6 squared. Okay, we know that's equivalent. It's just going to save us one step in writing things out there. So either way, what we get is 2 squared is 4, 6 squared is 36. So square root of 40, which we can reduce, right? Because 40's got a factor of 4.
2 squared root of 6 equals square root of 2. 2 square root of 10.
Say again.
6 square root of 10.
Right. 6 root 2 is too big. It shouldn't be that big. It's been too long since I simplified square roots. My goodness. So 40 has 4 and 10. Yeah, and 10 is not perfect square. So 2 squares is 10.
It's good to see.
That was harder than it should have been. So since 40 is the same thing as 4 times 10, 4 is a perfect square, you can factor that out. 10 is and it has a purpose for factors, it'll stay there.
Well, you didn't think it?
And I will tell you that when you're working with your fancy calculators simplify this stuff for you. I don't know how many of you have a fancy calculator at this point. Let me see if I can pull mine up real quick.
What calculator?
Yeah, 89.
I can't hear you.
All right. Oh. On the TI-89 calculators and Fantasy calculators, they simplify a lot of stuff for you. So the interface is a little different. Again, I didn't say you had to have one of these, but I encourage you to rent one or find something that's similar here for something like this. Anyway, they do simplify square roots for you. So if we take the square root of, what do we have, 40? Okay, it'll automatically reduce it down, which is something that TI-84s generally don't do by default. So 2 squares 10 just kind of verifies it there. Again, I still say you don't have to have one of these, but it may be useful to look into renting one if you don't want to buy it yourself. All right, either way, does that equal 1? No. So this is not a unit vector yet, which we're not too surprised. If you just think about the shape of this triangle, obvious, or the shape of this vector, obviously length is more than 1 there. So need to make it a unit vector. So to make it a unit vector, we say, okay, well, right now this vector -2, 6 has a length of 2 squared 10, which is too long. So we are simply going to multiply by its inverse. So we're going to have the original vector, and we're going to divide by that length. So same thing as multiplying by its inverse. There are a lot of ways we can simplify this. As long as we do one of them, I'm okay. Always simplify your answers. Okay, in any math class, reduce them down here. Don't leave it this way. One thing we could do is we can say, okay, well, we're essentially multiplying by that fraction, that complex fraction here. So let's just multiply each component by that fraction, or divide each component by that expression we just got there. Okay, this is one step closer towards a nicer way of writing this. Still haven't simplified it yet, but that would be equivalent there. Okay, how can we reduce both of these? What factors does those first term have in common? 2. So definitely reduced by those. So we -1 over root 10. And then something over here also have factors of 2, so 3 over root 10. Okay, that would be a fine way to leave this answer. There's nothing wrong with that. Okay. And that's probably the way I'll write it most commonly. But there are some other ways we can do it, and I'll look at those real quick here too.
So take out the 2, just take out the 2.
Right, so from the very beginning, basically that's what I was going to say. From the very beginning here, if we go back to think about this step here, okay, we can still think about like taking out the 2 just at this point, so the other point. If that vector -2, 6, both those terms were a factor of 2, we can think about factoring that out. So taking this longer vector and basically making it shorter there, and that would be a fine way to do this also. It's a little less conventional, but it still works as well. So we can think about this as 2 times, that'd be -1, 3, all over 2 root 10. And the same thing happens to 2 is canceled out there. We can go back and divide by the square root of 10. So there's a lot of different ways we could think about simplifying this. I'd probably follow that first path that I did when I worked through this, but just know there's a lot of ways you can work through this. Okay, just always reduce down as much as you can. Okay. So we are essentially done. We still have to go back and check that it has a length of 1, which won't take too long there, but that's a unit vector right now. If we were to graph this vector, and I'm not going to try to sketch it accurately on here, but if we were to go back and graph this vector, it would have the same direction as our original vector. It'd just be much shorter because now it has a length of 1 instead of a length of 2 times root 10. To verify that the length is 1, and I know I'm out of room here. Hopefully you guys have a little bit more. We simply go back and just find the length of this vector again. So to find the magnitude of our unit vector, like I said, we know it starts with the origin, so I'm going to kind of skip that step that we go through and subtract. We're just going to take each component squared and add those together. So this is going to give us 1 over 10 plus, oh, I forgot to write my square there, plus 9 over 10, which is indeed 10 over 10, which is indeed 1, which is what we expected to get there. Most of the time, you won't ask to be verified. It'll just say, find the unit vector with this direction, and you just can end where we have that little blue box there. You don't have to go on to the verify part, but just since we're new with this, it's good practice to go back and find extra links there too. Questions? I would strongly encourage you to try the homework once you get in there, or at least go back to the problems in the notes and try them on your own to make sure you can replicate it if you don't have the access to the homework yet. This isn't difficult to work with vectors, it's just, so if you can build your confidence now and make sure you really understand what we're doing in class, it's just gonna make everything else a lot easier. Because it's, like I said, it's not that we're doing difficult math at this point, it's just different ways of doing math. So the more confident you can be with it early, the easier it'll get as we keep going through. Okay, but that being said, please make sure you guys ask questions. I know, like I said, it's a little delayed on the camera, but I'll still hear you if you ask them. All right, so I'm ready to talk about this a little bit here, but we're going to elaborate on this. So the unit vector we just found, this guy over here, we'll approximate him in just a minute. We're going to go ahead and sketch a plot of it. And just because I know it's coming up on this graph, let's go ahead and count each block by 1/5 or by 0.2. So this would be 0.2, 0.4, 0.6, 0.8, and 1. Okay, it's just going to make our vectors fit nicer on here. All right, so the vector we just found, we had -1/√10, 3 over square root of 10. Oh, and I will say too, I don't care about rationalizing. Leave a square in the denominator, that's fine. It doesn't matter to me. If you like it, getting it out of there, go for it, but I'm fine if you leave squares in the denominator. Okay, if we were to approximate this, this is the same thing as about -0.32 and 0.98. If you just get decimal approximations for those, just a little easier to graph. So let's graph that guy over here. So -3.2 and then almost all the way up there to 1. So about like this is that vector. Okay. So it's nothing too exciting right now. Well, let's plot a couple more unit vectors. And down here I give a couple of them, although I'm going to change this one because this one's really similar to the one that we just looked at. So let's instead say -√2/2, -√2/2. That one looks a little different. The other one's fine, you can graph it, just this one looks a little different. But same thing, let's go ahead and just graph these vectors and plot them on here. So square root of 2/2 is about what? What is that as a decimal? Oh, another thing too, if you are working with these other calculators here, they work in exact mode, and I'll show you what I mean now. So if I want to take -√2 divided by 2, I know it's kind of tiny, but when I click enter, it says, hey, it's -√2/2, or to check the negative sign. It doesn't give you an approximation for it. If you want to get the approximation for it, there's this little diamond key over here. I don't know if you can see that very well, that green one. And then if you hit the enter key, that's going to give you approximations. So if you do get a chance to use one of these, there are some things that are a little bit different there, but you can get approximations. So about 0.7. So let's graph this guy as negative, sorry, to give a little bracket, -0.7, -0.7. All right, to put those guys on there, -0.7, 2, 4, 6, 7, 2, 4, 6, about over here. If we graph this other one, 2.4 is somewhere over here. 2, 4, 6, 8, 9 is close to up there. And you might not really notice much at this point, but if we keep plotting more and more unit vectors, what do you think is going to happen? They could. Well, let's do this. What's another simple unit vector? If we just go a unit of 1, say, along the positive x-axis, that's still a unit vector, right? So let's say we have the vector just 1, 0. Okay, just 1 unit along the x-axis looks like this. Okay, similarly, we can go 1 unit up on the y-axis. We can go 1 negative direction, negative direction. Think about the endpoints for all these guys. If we were to keep doing this for like the next 20 minutes, which we won't, what's going to happen if we think about the endpoints for all these vectors?
Will it make a circle?
It will make a circle, and what circle will it make?
The unit circle.
Okay, there's going to be a lot of connections between when we're working with vectors and working with three-dimensional stuff and trig, and namely just the unit circle. This thing does show up quite a bit here. But if you think about it, I mean, we're basically just defining the unit circle a different way. A unit vector in component form starts at the origin, which unit circle is centered at the origin. All these vectors in component form are going to have a length of 1. Basically, the radius is 1. We're basically just drawing a whole bunch of little radius for a unit circle here. So, like I said, you're going to see a lot of connections between what happens when we're working with vectors and working with this three-dimensional stuff and things we already know, okay, namely trig. If we continue to plot vectors, what would happen? We get the unit circle. And that's going to come back up in just a little bit here too, the idea of the unit circle. All right, but mostly from this page, unit vectors have to have a length of 1. Component form, we know means start at the origin there. Okay. So next page talks about standard unit vectors. I'm going to leave it here for just a minute because it's kind of already hinted at. What are the simplest unit vectors you could probably think of? Think in terms of like simple numbers.
1 and 0.
Yeah, just 1 and 0, this guy that's written in red here, right? If we just go 1 unit in the x-axis and nowhere up and down, it's a very simple unit vector. And then similar, if we just go 1 unit up on the y-axis, very simple unit vector there. Those are the standard unit vectors. Okay, and so what we're going to see is an alternate way we can describe vectors using numbers. And sometimes it's more handy this way, sometimes the other way, but the simplest unit vectors we can work with are 1 unit in the x direction, so in component form, that's the vector 1, 0, and then just 1 unit in the y direction. Which is just going to flip those around. We're not going anywhere left and right, so 0 for x and 1 for the y vector. Okay, so those are the standard unit vectors there. The names they often get, and again, these are bolded here, so if you want to draw little arrows on top, if that makes it easier to see what's happening, go for it. But I is what we call the vector in the x direction, and j is what we call the vector in the y direction. It's just still alphabetical. If we think about our properties of vectors that we mentioned a little bit yesterday, being able to stretch these guys and shrink these guys multiplied by a scalar, adding and subtracting them together, what this allows us to do is take any two-dimensional vector, whether it's got negative components, positive components, 0 components, whatever direction it's facing, and express it not only in component form, which we've been working with, but also in this standard unit vector form, which doesn't really have a short name there. So for example, if we have the vector 9, 11, okay, fairly simple vector, nothing too crazy about that. What we'd like to be able to do is write this guy as a combination of the I and j vectors. Okay, so it's going to look more like a sentence, a math sentence, than an actual vector here. So we can break it down this way. Okay, if we have this vector 9, 11, that can be the same thing as taking a vector that moves us 9 units in the x direction, plus a separate vector that moves us 11 units in the y direction. Okay. Does that make sense that we can do that? Whether you algebraically think about it or geometrically think about it? Okay, we're basically just saying, okay, to get to this vector 9, 11, you move over 9 on x, and then you move up 11 on y, which is what the addition tells us. Okay. From here, we can say, okay, well, for this first vector, we can factor out that 9. By factoring 9 out of this vector, what's it going to leave us with?
1, 0.
Yeah, 1 and 0. Okay, which essentially is just saying if I have that standard unit vector, that one vector in the x direction, multiplying by 9 just stretched to the factor of 9 there. So again, whether you algebraically think about it or geometrically think about it, hopefully that kind of makes sense. And then similarly over here, we can factor out an 11. Now leave us with 0, 1. And then hopefully that kind of makes sense why we can write this linear combination of vectors here. So what we just defined, this vector 1, 0 is the same thing as that I vector. And this vector 0, 1 is the same thing as the j vector. So this is an alternate way to go through and write this vector. Okay, it is longer, but it's got some benefits. You're not going to have to go through and do that 2-3 steps in between. I mean, it's fairly obvious. 9 is the x, stick an I next to it. 11 is the y, stick a j next to it, put a plus sign in between them. But that's kind of why we can go through and do it that way. Okay, so it just gives another option, another way we can work with vectors. Like I said, sometimes it'll be more useful, sometimes it won't be as useful, but it's just different ways to go through and do it. So there's kind of a summary of it. Usually the book's been called a linear combination of I and j, which is such a long, lengthy name for it. But you know what linear means, you know what combination means, and now we know what I and j are. Okay. So if we're similar things before, just kind of manipulating the vectors in this different notation. So we have u with the initial point of 2, -5, and a terminal point of -1, 3. And then we are told v is a combination of the I and j vectors. So two totally different ways to express the vectors here. We want to go ahead and answer parts A and B over here. Okay. So first of all, part A wants to know u. What is vector u? How are we going to find that? What are we told about u right now?
The initial point is the point.
We're told the initial point and the end point here. So if we want to visually think about that, which again, we don't have to, but we sure can. 1, 2, 3, 4, 5. We know this guy starts over here, and then -1, 1, 2, 3, it ends over there. Okay. How can we find component form for this? Because that's a nice common ground to work on. How can I find the component form of this vector? What we said yesterday.
It's terminal point
Yep. So the idea is we're basically going to try to take this point and move it over enough units to get to the origin. So this is going to have to move 2. And then we're going to try to move it up enough units to get to the origin. So that's going to move up also. So terminal minus initial is what it comes down to. So we're going to have -1 minus 2. And then 3 minus -5. So that is -3, 8. And there is the component form of vector u. Hear the buzzing to your linear combination of I and j. How can I write this as that linear combination of those standard vectors? What would it look like? For the same vector, still working with vector u. I want to write that as a linear combination of I and j.
So it would be 3, 0, 0.
Well, we don't have a 0 yet because we're still working with this vector. It's got an x component and it has a y component, so no zeros yet. We want to write it as this linear combination so that it looks more like this is what we're aiming for now.
So -3i.
Oh, -3i, 8j.
Yep. There we go. And make sure you put those little vector symbols above your I and j. Don't just write I and j. I and j on their own are variables. We're talking about the vector I and the vector j. So I'm not going to expect you guys to write in bold, although if you really want to, I guess that works too. But the little vector symbols above is what we're going for. Okay? So these are the same thing. In component form and standard form, they are the same vector. And unless a problem specifically says to write it in one way, I really don't care which way you write it. Whatever makes more sense to you is a good way to do it, unless the problem specifically says to do one thing or the other here. Okay? All right, for W, we just have a combination of all this stuff here. So we've got a lot of options how we can go through and write this. Since we have B given to us in standard form, that linear combination form, and we now have U in that linear combination form, let's just leave it that way. So we're going to have 2 times U, which we just found is -3i plus 8j, and then minus 3 times V, which the problem told us is 2i minus j. How did we simplify this?
Distribute.
Yeah, it's pretty much just like an algebra. Distribute and combine like terms is really all we're doing. So we're going to have -6i plus 16j minus 6i plus 3j. And then think that you're just doing these things together. So just give me a bunch of directions. We're going to go -6 units in the I direction. And then later on, we're going to go another -6 units in the I direction. So when we combine these two terms together, we have -12i. And similarly for j, we're going to go 16 units in the j direction and then our 3, so plus 19j. And that'll be it. If you'd rather work with those in component form, I'm fine with that. Okay, I won't go through all of it, but I'll just set up what it would look like. Okay, if we're going to do this problem in component form, U we already have in component form, so we'd have 2 times -3, 8. Oops, see the right symbol here. And then minus 3 times, now V isn't given to us in component form, but what would this vector V look like in component form?
It would just be 2.
Yep.
2, 0, 1.
Well, no zeros, remember, because right now we have an X component and we have a Y component, so no zeros.
Oh,
Okay, zeros are only for missing component, which I'll talk about in just a second here. Okay, we can work it in this way, and that would be the same thing. You're still going to go back and distribute, and then after distribute, you're going to go through and combine like terms just like we did before. Okay, so you end up with the same thing there, just look a little different. Now, mention the thing you just said about zeros there. Let me, I don't think I have an example coming up quickly with this. No. So let's just throw another example here. So say in component form, we've got the vector 3, 0. Okay, and you can picture it starts at the origin, 3 is the x direction, and it stops there. Does this vector have a y component?
No.
Yeah, I mean, 0 doesn't really contribute anything. It's not going anywhere up and down. So if we write this one as a linear combination of I and j, what are we going to get? We're going to have 3i and then nothing. I mean, if you really want, you can write plus 0j, but 0 times anything is just 0. So just writing this thing as 3i is all we're going with. So that's really the only time 0 is going to contribute to this. If there's nothing, no change in that direction there. In that component form, you have to keep 0. Because component form is more like an ordered pair. You have to tell it what's happening. If you just leave it blank, well, we don't really know what's happening there. In the other form, it's more like variables, and 0 times anything is just going to go away there. But again, these are equivalent vectors. This vector here and this vector here are the same things, just different ways of representing them. Okay? But again, if you try on the homework, there's more practice with this in the homework, and you can kind of see if you're getting it there. Okay? Questions?
Yeah, I do have a question.
Okay, what is your question?
With A, we started by saying component form. That is where I was lost a little bit. And then we have the -1, -2, 3 plus.
Okay, so like where those things come from?
Yeah.
So when we were doing component form back on page, oh, my computer stopped responding. Hold on just a second. We'll wait for OneNote to cooperate. I guess I could talk about it while it's waiting. Back on page 3, towards the middle of the top, we said that in general we can find the component form of vector by doing this. So what we're going to do is we're taking that endpoint for that vector and we're subtracting off that initial point for that vector. So this is still loading, but on the problem that we just did, the endpoint for this vector is at the point -1, 3. And then the starting point is at 2, -5. So if we want to find what the component form is, that -1 came from the x component of the endpoint, and then the 2 came from the x component of the initial point.
Oh, okay.
So does that make a little more sense? So yeah, there's the part that I was talking about. There's kind of our directions as to how to find that component form. But then the problem we're actually doing, next page. Okay, where all those numbers came from. That 2 came from over here, and then that -1 came from this point over here.
Okay.
So is it easiest to go in component form when you're trying to find a linear combination first?
It probably depends. I like component form better because there's less stuff to write. I think it makes more sense. It's clear. I can put my zeros in where they go. I don't have to keep track of my i's and j's. If it just seems like an extra necessary step, you don't bother doing it. I would say that it's not mandatory, but I do think it's easier to go that way.
Okay, that makes sense.
Okay, good questions. Oop, that's much bigger than I meant to be. Right, other questions? Okay, then let's flip to the next page. All right, so back to the unit circle. More trig stuff here. Like I said, it shows up a lot, so we'll see it a whole bunch of times here. Think way back to when you first learned about your unit circle and radians and trigs. If you wanted to draw an angle, and we'll just for sake of everybody on the same page, say theta equals pi/3. What's that look like? How do we draw a unit circle?
It's gonna be the
Yeah, it's a third of the way of half the circle, right? How many radians does one whole revolution have? Radio. So we know that half of that is going to be pi. So we know we're 1/3 of half of the circle there. So about over here. I don't have to be too exact. Remember, we always measure our angles from the positive x-axis. Okay, so from the positive x-axis, then moving counterclockwise around that circle, that's how we tell our angles here. Generally, then, that means negative angles would go clockwise, and all those same conventions work here. Also, by default, keep working in radians. Okay, degrees are fine. There's really nothing wrong with them, but if there's nothing said, then default to radians, just like normal. All right, so we have this. We know that right now, if we think about, let me erase this part here. If we have just this little pink line, it's a vector, right? Starts at the origin, goes to some point. What point does this go to? If we are still working with pi/3, what point does this go to? Remember the point it points to? Well, one. It has a length of 1, but doesn't point to 1. This is pulling on a little bit of your trig stuff here. Remember, we're making triangles in trig? So we're going over to this x component. What's this distance given by? Remember what we used to find that? Right, that's the cosine. Remember that x component is the cosine, and then that y component then is the sine.
Yeah.
So another way of asking the question is, what is the cosine of pi/3? And the sine of pi/3. So the point that this vector ends at is 1/2 square root of 2, which means super easy to find component form. Just change those little parentheses, brackets, or braces, whatever you call it, angle things, got component form here. Okay, so remember all that stuff from the trig. Your x component is your cosine, your y component is your sine, and that really allows us to take any theta angle here, okay, any angle we're working with for theta, and quickly be able to write a component form vector for that, or component form of the vector that that thing creates here. So that's really all this is saying right here. So this little default thing right here is basically just saying that u is still going to be a unit vector of a length of 1. If we have some angle that we know we're working with, we can quickly find the vector this thing creates just by being able to find the cosine of that angle or the sine of that angle. So for those default trig angles, we should kind of know those or at least know how to find them, but we've got this basic relationship here. Okay. In your standard linear combination of standard unit vectors, it looks like what it does below that. And again, I'm not going to be too picky on which one you go through and use here. Problem is, what is the magnitude right now of this vector? Let's just go ahead and find it. Oop, that is a V. I meant to write U. So let's find the magnitude of that vector real quick here. We have, again, it's in component form, so who cares about subtracting zeros? Don't worry about that. We're going to have the cosine squared of theta plus the sine squared of theta, right? So just the x component squared times the y component squared. But what does cosine squared plus sine squared equal?
1.
No, not tangent. It equals 1, right? It's like the best trig identity in the world, okay? And the square root of 1 is just 1. So any of these vectors we're making, if we're just sticking with the unit circle, which again, we know unit circle's radius is 1, everything here is just going to have a length of 1 there, which isn't very realistic. Most vectors don't have a length of 1. If we're talking about making some angle from that thing and trying to represent the angle of projectile, it's not just going to end in 1. There's going to be more to it than that.
I have a question.
Yes, Stephanie.
Since we know that the radius of the unit circle is 1, did we even have to go through
Nope.
that?
If you recognize it was 1, that'd be cool if you just said 1 because of that. I'd be fine with that too.
Okay, sorry, I was just double checking.
Nope, no, that's good. Double check that kind of stuff. I'm happy with that. So then being able to take that where we're stuck with a radius of 1 because of the unit circle or because of this process, we want to just be able to say, okay, we'll make it any length. Well, how do we change the length of the vector? What do we do to the vector to change its length? Scalar, multiply by a scalar. That's all this is doing here. So if we want to be able to cover any vector with any length, we're just going to multiply by some given length here. Okay, the magnitude of a vector is a scalar. It's just a number out there. So really what this allows us to do is say, okay, any vector that we are working with, we can write as this trig-looking function here. In component form, we'd have some magnitude times the cosine of theta, and then that same magnitude times the sine of theta. Okay, or if you like that linear combination better, pretty similar, you're still going to have that magnitude times cosine theta in the I direction, plus that magnitude times sine of theta in the J direction. Okay, again, mean the same things, just two different ways of showing it. In general, what makes more sense is what you should stick with, but kind of recognize both of them. If you do think back to trig, this has a lot of overlap with stuff we talk about in trig classes here. I don't have it linked quickly, but one way we define sines and cosines isn't just in terms of unit circle, but sometimes you have that r third in there. Same thing is happening here too. Okay, that r, that radius is what that length, that vector is supposed to be telling us there. And if you don't like looking at it when it has the magnitude of v, since that is a lot to work with, just think about this as just some scalar. If you'd rather just read it as like c, that's fine too. Okay, I'm not going to be super picky on your notation there, but it's just some number, some length that we allow this to be shorter or longer than 1 or shorter than 1. That's fine. So this we will come back to. So this was important, but this is something we will see later on. So I'm going to highlight that one instead. All right, you should have all the information you need for number 6 here. So instead of listening to me go through one more problem, you guys try this one and I'll walk you through the next one there. So give that a go. Knowing that we have a vector of magnitude 5 that makes an angle of pi over 3 with the positive x-axis, so something we just talked about. Write v is a linear combination of unit vectors I and j. So basically, write that vector out. I would say too, maybe write component form for it also, just to get used to doing both forms there and seeing the similarities. Like cosine of pi over 3 is 1/2.
Oh.
Right?
Oh, so we.
Right, so yeah, so you know the value of this. Yeah. And so you do the sine of pi over 3.
That is how.
Oh.
X to cosine. It's all capital X, pi and cosine all come first. So pi and pi. All right, so what did we come up with? Anyone want to share? What do we get? Go ahead, Russell.
Cosine 5 over 2i plus sine 5 pi over 3j.
I think you distributed them wrong. You're on the right track though. Back up one step. What'd you have before that?
5 cosine 1/2 I.
Back up one more even. I see what you did there.
5 over 3 plus, I mean,
I'll show you what you did. You've got all the right numbers, just put the wrong spots there. What is the cosine of pi over 3?
1/2.
It is 1/2. So all of this is going to be replaced by 1/2. The
Oh.
cosine just goes away. It's just been summer. Just blame it on summer. I know you know that.
5 halves I
Yes.
plus 5 pi over 3.
I plus 5 square root of 3.
Okay. Yep. And then if you like component form better, you can just strip off the I and J and write it like this. I know this one asks for linear combinations, but still, there's component form. Okay. So it's essentially just plugging into the formula up above there. But if you think about that picture, you've got some vector that has that pi over 3, it has a length of 5, and really we're finding what is that x component, that length, which is based on the cosine, and what is that y component, that height, which is based on the sine. Okay. All right, one more thing. Let's get through these 5 minutes, and then if we've got questions and time, I can do it today, otherwise tomorrow. This video I will wait for tomorrow, or if you want to view on your own, go for it. It is just, I don't know, I think it's entertaining, but we'll get back to that tomorrow. We don't have time for it right now. All right, so I used to put the picture in here. Picture gives too much information, so we're gonna draw that picture ourselves. So let's say we've got 2 tugboats that are pushing on an ocean liner. The details I'll give you in just a minute. And we know each boat is pushing with the same amount of force. We have a 400 pounds of force each boat is pushing on. Each boat is also going to be pushing at similar angles here, let's say. So the goal is we want to know what's the resultant force on the ocean liner, and then we'll also say in what direction. That way we know we're talking about that. So here we go, a little picture. Let's say we've got some ocean liner. I don't draw well, so simple little blob. Okay, and we've got some tugboats that are pushing on it, so I'll draw some smaller little blobs off to the side here. Here's my tugboats. Okay, and we know that these tugboats are pushing on this ocean liner. Each one of them is pushing on this ocean liner with 400 pounds of force there. Okay, so if we make the angle these guys are pushing at the same, then what direction should we expect this tugboat to go in? Sure. Just straight ahead, right? If the angles were going to be different, or if the forces were going to be different, then that would make the ocean liner go off in different directions here. Okay, so again, try to think about like geometrically what's happening here, and don't just do the math for this, because I don't want you to be in math class. But let's say that this angle with the horizon here, well, let's draw it up here actually. Let's say if we have this angle with the horizon, this is going to be negative 20 degrees, and let's say this one here has a positive 20-degree angle. Okay, so if we want to know what the resultant force is on the ocean liner and in what direction it's traveling in, we're basically saying, okay, well, the ocean liner's not doing any work. The tugboats are doing all the work here, which is crazy if you think about it. Like these little boats are doing all the work, which is pretty cool. But anyway, we're going to say, okay, well, what is the vector for the first tugboat? What is the vector for the second tugboat? And when we add those 2 vectors together, that's going to tell me what's happening to the ocean liner. So let's do that. Let's call this tugboat 1. We need to find a vector for that guy. And we're going to call this tugboat 2. And we need to find a force vector for that guy. Okay? So what we just did is basically the same thing that's going to be happening here. So for that first tugboat, we know it has 400 pounds of force. That's like that length, that scalar. We're going to go through and multiply this time. Okay? And then we're going to say, okay, well, what vector represents the direction this tugboat is going in? So basically this little line right here is what we're trying to represent. Well, like we just said, cosine tells us the x change, sine tells us the y change. So we really just need the cosine of the angle, which is negative 20 degrees, and the sine of the angle. Okay. I wrote that slightly different. You can distribute that 400 so it looks more like the format we used in the previous page, but hopefully we can see it's the same thing. Okay, I just had the 400 out front instead of distributing. But does it make sense why that fits into what the first tugboat does? Okay, and then similar for the second tugboat, we're going to do basically the same exact thing, only we're going to have positive 20 instead of negative 20. Okay, so that tells what each tugboat is doing. And like I said, the ocean liner is just sitting there doing nothing. The tugboats are doing all the work. So if we sum together the amount of work with the force that each of these guys is applying, then that's going to tell us what's actually happening to the ocean liner. So really all we need to do is go back and take force 1 plus force 2, and that's going to tell us what's happening to the tugboat. Or to the ocean liner, I'm sorry. And since we are very close out of time, I won't sit here and go through and push buttons in the calculator, but if you just use your calculator to approximate this stuff, 20 isn't one of those nice angles that has easy numbers to work with here. What eventually happens with this, I didn't even write down the in-between stuff I did in my notes there. When we add both of these guys together, I'll just give you what we end up with. We get 751.8 for the x component and 0 for the y component. So what does that vector mean? What does that vector tell us? Like we said, just straight line x direction. There's no y direction variation there. And if you think about it, it makes sense. The sine component is just going to cancel out. One's positive, one's going to cancel out there. Okay, but then we can also see how much force is actually being applied on that tugboat. Even though each, or on that ocean liner, either each one is doing the 400 pounds, some of it is getting canceled out since we're pushing against each other. Okay, so to try to start to get at how some of this applies to actual real world stuff, there's a fairly simple package.
Quick clarification, that in between step is distributing 400 and then adding the cosines and adding the sines.
Right, yeah. So what we would do is we distribute this to both terms inside of here for both of these guys. And then 400 times cosine of negative 20 is whatever. Add that to 400 cosine of positive 20, and that's what the 751 comes from.
So since we know that, I guess we don't.
Yeah, but if you can see this just going straight, then just.
I'm just saying, like, sines, should they cancel pretty?
If one's off by just a little bit, now if we have, like, say, negative 19 degrees and 20 degrees, they're going to be really close to 0, but it wouldn't cancel out. I'll try to remember to come back to this tomorrow and actually put the numbers in there. Maybe change it a little bit. But yeah, hopefully the general idea kind of makes sense at this point. Okay. All right. I know we're really close to out of time. If you guys have questions and want to hang around now, I do have a class in 5 minutes where you can answer them. Otherwise, tomorrow we'll go ahead and do all this stuff. Those of you who haven't gotten a WebAssign yet, try to get into that. So those of you in Stewart, see if you can get in there and get that working out there. And then we'll just keep dealing with the issues as they come up. Okay. So I'll see you guys tomorrow.
I have a question. Is the code?
Yes. Sorry. I couldn't tell. Go ahead.
Yeah. For our quiz tomorrow, how is it going to be like online?
For your quiz tomorrow, good question. It's not going to be so much this stuff here. The quiz tomorrow is going to be more like doing the stuff like we did over here, working with adding and subtracting vectors, and then there's a little bit of unit vector stuff on there too. So it's more the algebra part of what we've been doing, not that trig stuff. There's none of the trig stuff. Okay?
So, yeah, I was asking, is it going to be like online or we have to?
So what I'll do, and I'll just even show you kind of what it'll look like. Don't look too hard at the answers here or the questions here. I'll just put this up on the board, the quiz problems, and you'll just work them. And then what I've had students do in the past is like send me a picture of their work. We'll see if that works tomorrow. So as long as at least one of you has a cell phone, just send me a picture, give me an email, and then we'll just do it that way. We won't worry about doing these things online. It's kind of a pain to do things around time. Okay, but yeah, tomorrow I'll make sure that's more clear, and if it doesn't work out, I'll figure something else out.
All right.
Okay.
Thank you.
All right. See you guys then.